In this video, we're going to introduce the concept of isomorphisms with some examples. Alright, let's consider the following two groups. On the left-hand side, we have the group that I'm going to call V. It is the symmetry group of the rectangle. So we've seen this group before. It has the horizontal line of symmetry, the vertical line of symmetry, and a 180-degree rotation. And here was the multiplication table. On the other hand, some students got to compute the units for multiplication modulo 8 and the corresponding group. And here were the units. They were 1, 3, 5, and 7. And so these are the numbers such that when you're working with multiplication, modulo 8, they actually have inverses. In fact, in this case, they're their own inverse. And it happens to be that H, V, and R are also their own inverse, and so you see the identity element down the diagonal in both tables. The other property you see these two tables both have in common is that if you take any two elements that aren't equal, and neither of them are the identity, when you multiply them together, you get the third element, or the fourth element in the set that's not the identity. And in fact, this is actually true always. H times V must be R, H times R must be V, and so on. And this also happens to be true for this multiplication table. So you can check. It's a pretty cool fact. Or at least I thought it was cool the first time I observed it. And so these two tables have a lot in common. They both have this property. It seems like there's some sort of sense in which we could say they are the same table. But, they really, in one sense, they aren't, because, these symbols are telling you that these are transformations of the plane coming from the symmetries of the rectangle. And these numbers are telling you you're dealing with congruence classes modulo 8. But remember, the definition of a group is a set with a multiplication operation on it. The fact that these elements happen to have extra structure, and these elements happen to have some sort of extra definition, are not related to the fact that these are groups. So if you want to talk about groups, well, there should be some way to say they're the same. And there is, and that concept is called isomorphism. Namely, if you define a function from EHVR to 1, 3, 5, 7 in the following way. You send E to 1, H to 3, V to 5, and R to 7. Then the column labels get replaced with the column labels on the right. The row labels get replaced with the row labels on the right. Moreover, all the E's got replaced with 1s. These two H's and these two H's both get replaced with 3s. These two V's and these two V's both get replaced with 5s. And finally, the anti-diagonal of R's becomes an anti-diagonal of 7s. So we see basically the point is, if I define this function at the level of sets, so just on the elements of the group, it's a bijection between the elements of here and the elements of here. But if I do this replacement at the level of the multiplication table, this relabeling, I replace the left multiplication table with the right multiplication table. So I really do see these groups are the same groups. So that a rose by any other name would smell just as sweet. As far as the group structure is concerned, it doesn't matter that these were rotations, and it doesn't matter that these are congruence classes. What matters is that the second row times the third column gives you the label for the fourth column. And that's true in both cases. And that's what isomorphism is, and that's the idea behind why we care about them, because it tells us to forget the extra structure and only care about the multiplication operation itself. So, in some sense, these two groups are the same. Here is the fundamental definition. An isomorphism, phi from G to H, so from a group G to a group H, is a bijection, satisfying this extra condition. So what this condition is saying is that when you take the Cayley table and relabel the Cayley table for G and relabel all the elements using this bijection, one by one, you will get the Cayley table for H. So for all x and y in the group G, phi of x times y is equal to phi of x times phi of y. This is sometimes referred to as saying that the function is multiplicative or preserves products. So I'll often say it's multiplicative. In proofs, this is what we write. So as I said, the intuition is you take your table and you replace all your labels completely by applying this function to every single entry in the matrix in the table at the same time. And then, so by that logic, what must go here is phi of x times y, because what was here was x times y. Then the point is that what you should get at the end of the day is the multiplication table for the right group on the right hand side. So this is telling you how to multiply that row times that column. And so one thing that's obviously not clear, so I can color code here, is that you start with the group operation in G, but you end up with the group operation in H. So this multiplication is in the second group, this multiplication is in the domain group. Finally, in case this isn't already an overload of terminology, we'll often say when you have an isomorphism that G and H are isomorphic, and we'll write G is isomorphic to H. You'll notice here, I'm not defining what a bijection is. There's two ways to show a function is a bijection. One way is to show it's surjective and injective. Another way is to construct the inverse function and show that this function is invertible. I will show you in this class another approach when you have a pair of groups that allows you to prove injectivity a lot sooner. Here's an example that's often given in textbooks, although most of the details are skipped. So the isomorphism goes from the set of real numbers to the positive real numbers. Here, the group structure is addition, and in the codomain, the group structure is multiplication. And the isomorphism is given by exponentiation. You take x and you replace it with e to the x. And it turns out this is in fact an isomorphism. So first we show that phi is a homomorphism. I should have mentioned this term before. This is another way to mention that multiplicative property. And often it's what I tend to show first when I do these proofs, because it's the new thing. So what does it mean to be a homomorphism? or to preserve the multiplication, well, you take two elements in your domain group, R, and you want to show phi of x times y is equal to phi of x times phi of y. In this case, our domain is a group with respect to addition, so when I said times, I really mean plus. So what is phi of x plus y? Well, it's e to the x plus y. Properties of exponents, e to the x plus y is e to the x times e to the y. So the homomorphism part is simple enough. The textbook, of course, skips the other parts because they actually require calculus. So this part is optional, but I like to include it because it's kind of fun. Why? Because, well, one of the other theorems is that, from earlier in the course, is that bijections are invertible, and the inverse of this function is the logarithm. This is the reason why logarithms are hard. So, of course, why is the exponential function surjective? For this proof, the things I'm going to assume, besides theorems from calculus, is that the limit of the exponential function as you go off to negative infinity is 0, as you go off to infinity is infinity, and that the derivative of the exponential function is itself. These two properties are not that hard to prove. This one actually follows from that one. So let's prove the function surjective. Well, what do you need to show? You need to show you need to take a positive real number, and we need to show that there exists an x since e to the x is such that e to the x is equal to y. Here's how we're going to do it. Since y is a positive number, and since our limit as you go off to negative infinity is 0, there must be some point a where e to the a is less than y. Also, since the limit as x goes to infinity, e to the x is infinity, there must be some point where where e to the b is greater than y. In other words, you've got some level y. Your exponential function has to be below that point eventually, and it has to be above that point eventually. Otherwise, you wouldn't have these two limits. If you don't understand the reasons why that works, you need to go back and review your definition of limits. Similarly, because we have this derivative bit, this function is differentiable everywhere and hence it's continuous. So we can apply the intermediate value theorem. There exists a point C between a and b such that e to the c is equal to y. Because we found a point where the function's above y and a point where it's below y, so there must be a point where it's exactly y. So that's right. The only reason we know the exponential function is surjective is because of theorems from calculus. Similarly, the only argument I know to show it's injective is through calculus, by using contradiction. Suppose you could find 2 points where phi of a is equal to phi of b. In other words, where e to the a is equal to e to the b, where a and b are distinct. Since we're assuming they're distinct, we might as well assume one is smaller than the other. Well then, by the mean value theorem, there exists a c between a and b whose derivative is 0. But since the derivative of the exponential functions itself, we're saying phi prime of c is e to the c, we're saying e to the c is 0. But that's not possible. So you have a contradiction. Ergo, this can't ever happen, and the function is injective.